Hello all, welcome to the video lecture series for the subject database management system. Now I am going to explain you all about what is storage structure in database management system, right? So basically I am going to tell you about the basic structure of database. So what is storage types in database? We have primary, secondary and tertiary, right? So basically these records in database are stored in file formats, right? Physically the data are stored, the formats, right? The data are stored in electromagnetic format on a device, as you all know that. So after this, the electromagnetic device used in database system for data storage are classified as primary, secondary and tertiary, right? So we are going to classify this form, right? Basically high capacity, right? So it starts from primary, secondary and tertiary. As we speak about speed, it starts from tertiary, secondary and primary, right? This is speed and this is capacity, right? If you want to balance both the speed and capacity, absolutely we need to refer, that is RAID, redundant array of independent disk, right? So in database management system, this redundant array, okay, of independent disk plays a very important role. Actually this RAID is a technique that combines multiple hard disks or SSDs into a single system to improve the performance. So why we need to improve the performance? Basically we require data safety or both of this performance and data safety, right? If one drive fails, if there is a performance and there is no data safety, if one drive fails, the data cannot be recovered. By applying this RAID, if one drive fails, the data can still be recovered from the others. How it is possible? We are going to see how this RAID is actually working, right? So here we can able to see the different levels of RAIDs, right? So actually how this RAID works, in one line data is not stored on just one drive, okay, but it is stored and distributed across multiple drives. That is how this RAID is actually working, right? So the data is actually split into smaller blocks, for example like dividing a file into chunks. That's a pause. These blocks are written across multiple drives in parallel. That is how we are going to show in RAID 0, RAID 1, 2, 3, 4, 5 and 6. See, this RAID 0 is explains about stripping. We are going to see with every RAID with example. And RAID 1 with mirroring. RAID 2 with bit level stripping with the dedicated parity. And here also the same, but it is bit level. Here it is byte level stripping with dedicated parity. And RAID 4 is not about bit or block, sorry, byte, it is about block. And RAID 5, it is about block, but it is not dedicated parity, it is distributed parity here. And about 6, it is about block level with distributed to parity, right? So it is actually started with a base and it is reaching the advanced level of data storage access in database management system, right? So we have a RAID controller here. Okay, what actually the RAID control does? Actually, the total different process of RAID is controlled by a RAID controller. RAID controller manages multiple hard drives. That is a process, making them work together as one system. So whatever the separation have you are seeing here, it is going to be always concentrated on making them to work together in one system. Because to improve the speed and add data protection by handling the drives which is failed. That is the process. Okay, so let me directly get into the types of RAIDs here. One by one we are going to see, right? So I am going to explain you all about RAIDs and its types with one simple example where you can able to understand very easily. That's the point, right? So actually what is RAID 0? It improves the system performance by splitting the data into smaller blocks and spreading, right? So here we used to call a name called stripping. What is the process of stripping? It enhances the data speed by enabling parallel read and write. For example, here there is a data 0, 1, 2, 3. 4, 5, 6, 7, 8, 9, 10, 11. Assume that these are all the datas. Okay, it enhances the data speed by read and write operation. Here you can see if you want to access 0, that is in disk 0. If you want to access 4, that is in disk 4. So each and every data is separated. So it is easy for any request in the database management system to access. Speedy access is there, but there is no redundancy. Okay, so this 0 is not saved anywhere in the different disks which have been stored in this particular table. Okay, so here the operation provides no redundancy, and also there is no fault, that is tolerance. Right now, so here you can see that I have mentioned some process about how to understand this. Reliability is 0. That means no duplication here. You can able to check. This is data 0, 1, 2, 3. There is no repetition here. What happens if there is no repetition? Once the data is lost, we cannot able to recover. Okay, so here you can see the data form a strip. For instance, what is a strip? 0, 1, 2, 3 all together in different drives. We used to call it as a strip. Okay, so that's why the stripping is adopted here. There is no duplication. The capacity here, you need to check the capacity. Right, what is the capacity process here? N into B. N is a disk, B is a block. Here the entire space is being used to store data. You can able to see here we have not skipped any of the blocks here. All the blocks is perfectly utilized. That is block B. Okay, so N, the disk 0, 1, 2, 3. So here you can see there is no duplication, and N disk each having B blocks are fully utilized. This is N disk, B blocks is completely utilized. Right, so here this RAID 0 is easy to implement. Easy storage utilization is adopted here. It's not a good choice. It is actually the benefits. You can take this as a benefit. What is the limitation we have? This is called as a limitation. So here it is not a good choice. Why it is not a good choice? A single drive loss can result in a complete failure of a system. Right, and also for a critical system, this kind of stripping is not recommended at all. Okay, so this is how this RAID 0 works. Let me take you to the RAID 1. We used to call RAID 1 as mirroring. I'll tell you why this RAID 1 is called as mirroring. Actually, it enhances the reliability. Okay, so what is that reliability? Here we created an identical copy of the element. By seeing this table, you can able to see that, and each data block on separate disk. Okay, so this ensures that even if one disk is failed, the data remains accessible from its duplicate. Say for example, original is data disk 1 and duplicates are D1. Here the original is D2 and duplicates are D3. If any of this is lost, we can recover from the either of the other drives. Okay, the data remains accessible from its duplicates. While this configuration is highly reliable, why? Because it requires significant storage overhead. Right, so here you can see the copy is available. One disk fails, we can able to recover from the other one. This is actually highly reliable. Why? Because if we face, right, if you face any disk failure, this is going to be a very important role to recover the process. Okay, so here you can see the limitation. Benefits you can see much here. What is the limitation? That is the disadvantage. It is highly expensive. See here, we have only two set of datas, but for this two set of datas, this is set 1, this is set 2. This set 1 and set 2. This two set of datas, we use two set of duplicate disks to store. Right, so here the storage capacity is very less when we compare to the stripping. Stripping is N into B, but here it is N is actually divided by B. Okay, N stands for disk, as you all know that. B stands for block. So we are lucky enough to use 0 or 2 fail, then it can be handled. Right, if any of this is block is failed, we can able to handle it. Right, though the capacity here you can see here, that is also be calculated. that is n divided by b, or else you can take it as n into b divided by 2. Both the options, the capacity of the space, right, being used here to store the data, right? So the other half is just a mirror. You can see this is actually a mirror, this is actually a mirror, just a mirror, right? So the data is not fully utilized here. However, this particular mirroring is very useful when there is a data is lost. Okay, I hope you understand this process, right? And also it covers complete redundancy. It increases the data security as well as the speed. Okay, so this is how this RAID 1 is actually working, right? So let me take you to the next level of understanding, that is RAID 2. The only difference you are going to see here, that is, this is actually a specialized RAID level that uses bit level stripping with dedicated parity, right? So before that we are talking about redundancy, we are talking about mirroring, but here we are going to talk about the stripping in each block with dedicated parity, right? I'll tell you what is a parity bit. To make this even or odd, we always use this Hamming code. Hope you remember how this Hamming code is working. This Hamming code is specially utilized here for error correction and detection using any kind of data to be configured. Okay, so here the data is distributed at bit level across multiple drives. I'll show you the drives as well. So the crossed disks are called filled one, and the other are called as parity drives, right? So here the distributed level across multiple drives and dedicated parity bits are used. Only purpose is to dedicatedly monitor and detect the error and the correction, right? Once the error is detected, the automatically correction is done. That is why we learn about this Hamming code mechanism, right? While it offers strong fault tolerance, right? This offers strong fault tolerance. It's complex. It is actually very complex, and cost make is rarely used in practice. That's why. Why? Because each and every disk you can able to see here that will have a separate disk with full of parity, right? So here, what is the benefits here? Strong fault tolerance it has, that is all okay, but the structure is actually very complex, and also it is very high cost, right? Why? Because a separate drive here used only for parity, right? So there is no disk here which is separated with data as well as parity. But here in this bit level stripping, that is RAID 2, there is completely the extra drives only for detection, error detection. This is the error detection drive 1, 2, 3. Right? So what happens here? Absolutely, the disks are completely used only to store the parity bit for recovering. That is to make the error correction and error modification. That is, we used to call it as in a distributed environment. Okay, error correction, absolutely. That is a perfect way we can match here. Right. So we'll move on to the next level of understanding, that is RAID number 3. Right. So what is RAID number 3? Initially we have done a bit level in RAID number 2. So let's make it as a byte level, because when we move on to the advanced stages, we need to look for the complexity of the algorithm as well as the data storage capacities. So here you can see this RAID 3 byte level stripping with dedicated parity is actually used for high throughput for sequential data access. That's the point. So here, however, it enhances the fault tolerance by employing byte level stripping across multiple disks, right? So here storing parity information on dedicated parity drive. That's the point. So instead of using multiple drives to store, as we all see here, multiple drives are used to store for just to store the parity bit. Here, one drive is dedicatedly storing parity bit for remaining drives. Say for example, the dedicated parity byte allows for the construction of the lost data in a single drive files. Say for example, we have disk 0, 1, 2 and 3. Disk 0 stores the datas and disk 1 and disk 2 separately, as you can able to see here. But in disk 3, you can able to see the parity is added for 15, which is stored in disk 0. Parity added for 16 that is in D1, 17 that is in D2. Here this D3 is dedicatedly performing the dedicated parity access. The configuration is suitable for workload and it is high throughput for sequential data access throughout the other disk which is randomly stored. And but here you can see that the less efficient for random input and output operation, but here it is not the case. That is in RAID number 2. But here RAID number 3 you can be able to see that efficient way of random input and output operations. Okay, so now you can see how this evolution process is done here. So here you can see the capacity may be, that is I'll do here, capacity may be n minus 1. Okay, n minus 1 into b. What is n minus 1? N is actually number of disks. Number of disk is 4, but one disk is dedicatedly allocated for parity. So data disk or n minus 1 is this particular disk. Okay, into b, but the blocks are completely utilized. Okay, so here n is the total number of drives, 1, 2, 3, and blocks is the number of block per drive. So we have 1, 2, 3, 4 across all the drives. The capacity of one drive is reserved for storing parity information. That is the disk number 3. Right? I hope you understand this process. Let me tell you what is the benefits of this RAID number 3. Right? Data can be transferred in bulk, number 1. Data can be accessed in parallel. This is all okay. But there is a limitation here. It requires additional 1 parity bit for number of disks. If you have 10 disks, 1 additional disk you need to have only for storing the parity bit. Okay, so in this case, it may, in this case, it may have a smaller size files. It may perform very slowly. If the data access, the parity bit checking, right? So it may require high performance database structure for very speedy access. That is how this RAID number 3 byte level stripping with dedicated parity works, right? I hope you understand how this RAID is actually working. Okay, let me take you to the RAID number 4. So RAID 3 was talking about byte level stripping. So RAID 4 is going to be explaining about block level stripping with dedicated parity. Okay, so here every data access, right, they are increasingly making the complex into simple, right? What is the complex in the previous RAID 3? If any of the data have very limited access or else small size, it may take much time to access the data, right? So here this RAID 4 is actually introduced. Okay, so RAID 4 is for block level, and also it combines a dedicated parity disk to provide fault tolerance. So here you can able to see the structure of it. So here the data is written in blocks and a separate disk stores parity information using XOR function here. That's a point, right? So instead of having all the disk data separately in one particular thing, here you can able to see this is the parity bit, right? So the parity bit is stored in disk number 4, right? So here the data is written in blocks, right? And separate disk stores parity information, which is calculated using XOR function, as I already told you. This setup allows our data recovery in case of single disk failure. That's a point. Okay, so here we are going to check the parity bit. If any one of the disk is failed, if the disk failed in multiple, this particular XOR is actually a failed process. Okay, let me tell you. If for example, I have taken the parity bits here, right? Assume that the bits, okay, say for example, the bits in D0 or D1 or D2 or D3, any of this, right? So I have taken that in a binary case, right? Say for example, bits are 0, 0, 0, 1 or 0, 1, 1, 0. Two case I have taken. I am going to calculate the XOR, that is D4 for this particular parity bit. So here you can see that parity bit in XOR here. That is first case, XOR of 0, 0, 0, 1. We are going to make that into even accessible. In this case, you can mention 0, 0, 0, 1. This is actually data. This is the parity bit. Okay. So what if you have a even number combination? right? XOR of this particular 0, 1, 1, 0 will become the parity bit as 0. So this two parity bits stored in D number 4, that is device number 4, as you can able to see that in the table which is already displayed here, right? You have a suggestion here, not suggestion, the evaluation process here, that is what we did in the previous one. Here also we have the capacity as the block is n minus 1 into B. Okay, this is the actual capacity, because block, that is here you can see disk 1 is completely used for storing the parity bit. Okay, and n minus 1, that is what I told you about. Okay, the blocks here you can able to check, that is completely used, but the disk you can able to check, that is n minus 1. 0, 1, 2, 3, 4. Fourth is actually used only for storing the parity, so it is n minus 1. What is n? Number of disk which is shown in this display, right? So this is how it is. What is the benefit here by using this RAID number 4? Any guess? So let me tell you, it helps in reconstructing the data if at most one of the data is lost. For example, if you can able to see here, if any one of the data is lost, for example, what is lost? This 0 may become 1. So what is the parity bit here? That is definitely 0, 0, 0, 1. The parity has been checked as 1. What if this data is lost, that is 0 into 1? Here you can check it. 0, 1, 0, 1. What will be the parity? How to write a parity for this particular thing? We need to write it as 0. But the actual parity is what? 1. So in this order, by using this particular Hamming code technique, we can able to recover which particular data is lost here. And we can recover that 1 into the original data as 0. This is possible if any one of this data is lost. If multiple losses occurred, definitely it is not going to work, right? So we are always looking for the advanced level of checking the parity and its accessible format, right? So this is how RAID 4 works, right? Let me take you to the RAID number 5. What is actually RAID number 5 here? You can able to check it. Block level stripping with distributed parity. Say for example, here in RAID number 4, dedicated parity has been adopted because all these parity bits are stored in one single disk. But here you can able to check the parity bits are stored in a distributed way, right? So what is the advantage here? Let me tell you. So here the distributed parity information across all the disks instead of storing in one, the distributed parity significantly improves the performance, especially for random write operation. That's the point. Okay, the randomly if you can write this particular data here and there in the devices located here D1, D0 to D4, there is no separate disk here which is particularly storing parity bits, right? So here the maintaining of fault tolerance for single disk failure. If any one of this disk is failed, that is not going to affect any of the other disk which is simultaneously processed. Okay, so here the reliability, performance and storage is very effective. That's a point. Okay, so let me tell you how does the example for how does this process work. Say for example, this is for what is like your understandability. For example, disk number 0. We have a data called D1 and D2. Okay, disk number 0 I'm talking about, right? D1 and D2, right? Disk number 0, data 1 and data 2. Any number of data in rows you can able to check. The parity has been arranged as P1. And for example, disk number 1. So here the data, you can able to check it. Data number 3 and data number 4, the parity may be P2, right? So each and every disk, right, there is going to be a known rule which is going to be XOR and calculate as we did in RAID number 4. We can able to do that at the XOR process, and we can able to store this in a different multiple disk, which is going to avoid if there is a failure in one disk, that is not going to affect the other one, right? So here, what if the data recovery, how does the data recover? In case of a single disk failure, right, the missing data can be reconstructed by XORing as we did in the previous method, right? That is data, RAID 4. The remaining data blocks and parity information can be easily recovered. That's the point. Okay, so what here also the capacity in RAID number 4, I'll write here. The capacity of RAID number 4 is n minus 1 into B. Why? Because you can able to check every disk D1, D2, D0, 3, 4 and 5. Randomly this parity bit is saved. You can able to check here. Randomly the parity bit has been. The block is fully utilized even though the number of the blocks are completely done. The disks are made available for data storage, right? But all space equivalent to one disk. All space is equivalent to one disk. So definitely n minus 1. Right? I hope you understand how exactly it works. So after looking into this process, you may have an idea what will be the benefits of RAID number 5. Right? The data can be reconstructed using parity bits. Absolutely, it is also there in previous RAID number 4 also. It makes the performance better comparing to the RAID number 4. That is the point you need to note. Because all the parities are saved in every drive, not in a single drive. So read and write operation actually becomes very, very easy. Now, what the limitation, that means the disadvantage we have here, right? So if the technology is complex, the space you need to have extra always. It is always required an extra base, right? The board disk get damaged. For example, if any of this disk is getting damaged, definitely the data is lost forever. Right? It is not only in RAID 5, it is always whichever the disk have parity bits, the disk is failed, then the complete process is lost. Right? So even though whatever we do for the minimal accessibility and also the minimal performance. If we go for the advanced technology, absolutely this process has to be enhanced, improvised. Right? So this is how RAID number 5 works. Let me get into the RAID number 6. So by seeing this table, you can able to differentiate what is the difference between RAID number 6 and 5. So here block level stripping in distributed parity, that is the previous one, but here 2 parity bits for one particular data. See here you can see disk 1, disk 2, 3 and 4. We have data A1, data B1, but the parity bit here in both the disks we are going to save for B1, parity of B1, parity of B1. Why? For example, if D3 is failed, we can recover B1 from D4. If here D4 is failed, we can recover B1 from D3. Hope you understood. Here it is an advanced version. It provides fault tolerance by introducing double distributed parity. What is the disadvantage here? It allows RAID to recover from failure 2 disks simultaneously. That is all okay. Making it more reliable for critical system. That's the point. So this RAID 6 will be used for very, very sensitive data. Right? Say I want to protect my data. I need to have I should not lose it in any of data crashes. I should not lose my data. So what I need to do, I need to go for RAID number 6, which have a double processing of checking. Right? So here the added parity calculation can impact with performance. That is all okay. But the reliable for critical system with larger arrays. That's a point. Right? So it is none other than having 2 parity bit for one particular data. Right? So what is the capacity here? Now you can able to check the capacity n minus 2. So we are using 2 disk for what? Saving the parity bit, not 1 disk. N minus 2 and the same process, the blocks are B into B. Right? So here the benefits are very high data accessibility, fast read data transaction, but the disadvantage is due to the double parity, it has very slow write. You cannot just like that write the data, right? The data transaction requires multiple check. Extra space is always required here, right? So this is how about data, RAID number 6, and the whole process here explains you all about how this data storage types in database management system is very effective in order to improve the performance, how exactly this RAID works. I hope you understand.